Yeah, and I don't know why it comes up like this unless I've got the wrong note up. Let's take a look. Yeah, and you can put the title naming acids and bases. Yes, if you've already done that, that's great, because that's what we're doing. Okay, so we're going to learn how to name acids and bases. Actually, bases we already know how to name because they all end in hydroxide, and we've already done ionic compounds where we determine, the formula or the name of a hydroxide. It is at the end of the note, but it is nothing new. Now, acids, and you can write this down, and don't worry about the asterisks that there are a few exceptions. It's a true statement, but you don't have to write it that there are exceptions. So acids, we came across it when we learned how to name other substances, and essentially acids start with an H because they've got that H on there that has to fall off in order to produce an acidic solution. And they must be dissolved in water in order for this to happen. For the H to fall off, it must be dissolved in water. If it's not dissolved in water, then it isn't behaving as an acid. The H's will not fall off. We've already encountered what it means when something is dissolved in water. We call it the aqueous state, AQ. And that's going to become part of our name. Because if an acid has to be dissolved in water to be an acid, then in part of our name, we're going to state that it's aqueous. So we're going to essentially learn how to name 3 different types of acids. And they're very similar in the method in which we're going to name them. Now, I've adjusted this note from what it originally looked like, and I've actually made it look a little more like my 3U note. It just makes more sense to me this way, and I can actually condense the note down quite a bit, because I find it doesn't make sense to write about how you name something. It's more practical to actually go about naming it and practice it than writing statements on how to do it. So don't write this next slide. There are 2 types of acids that we're going to name. It's called binary acids and oxyacids. And there's actually 2 little subgroups underneath the oxyacids. But there are 2 types, and we're going to put the title on the next pages anyway, so no need to write that down. So the first type that we're going to talk about, again, don't write this down. There are actually 2 naming systems in which we use. We use something called the IUPAC naming system. It's kind of like the newer naming system, probably invented around about 1930, maybe a little earlier, where a group of chemists decided to kind of, reorganize the naming system to make it a little more useful. There is an older naming system that was designed before the 1930s, and it was actually initiated by, and the cover has fallen off, by our guy Antoine Lavoisier. And in actual fact, in his book, right, there are certain pages or certain locations where he actually goes about telling his way in which he would name things. And this was done in the mid-1700s, and that's where the classical naming system comes in. You might say, why do we need to learn the classical naming system? It's such an old system. We still use this old naming system in chemistry. It hasn't kind of disappeared. So unfortunately, by creating the new system, we've now got to learn kind of 2 systems in order to name this. But it's not too bad. They're very much related to each other. So, binary acids. Now, in this chart here, you do not necessarily have to put the boxes and make it look like a chart. It's just really a list of some names. But if you need a ruler and want to make the chart, there's a ruler for you. But again, you could make 3 columns: formula, IUPAC name, classical name. Now, we're going to be doing naming. You're going to need your periodic table. If you have a periodic table, which most of you do, get it out now. If you don't have a periodic table handy nearby, I've got the periodic tables up here. You can come up and grab a periodic table. So the binary acids contain hydrogen and a non-metal. So we're talking about these guys on the right-hand side. And the non-metal, when we put that non-metal as a negative ion, they all end in "ide." So all of these things on the periodic table, fluoride, chloride, bromide, selenide, sulfide, phosphide, they can be converted into a binary acid. Now, when it comes to naming, I'm not normally generous in any way when it comes to, helping you on a test or a quiz. But I'm going to give you on the board this second bullet. And there's a similar bullet for the other acids. In other words, this is what it means. If whatever you're dealing with ends in "ide," like a fluoride or a chloride or a bromide, there's actually a special case here, CN. If you look on the back of your periodic table in the chart, that's called a cyanide. That's why it's involved. That's why it's part of this group. So if it ends in "ide" and you add H's, you'll notice I don't have that above my arrow, but you add H's to turn it into the acid, then the name becomes hydro, just like the electricity, hydro blank ic acid. So whatever the word was in here, like fluoride, that fluor goes in here to get the name. All right? Now this is the classical name. So if you want to put an arrow here, this is the classical name. That's how we get the classical name, hydroblankic acid. Okay? So I'm going to give you that tomorrow on the board when you have to do your naming. If the thing ended in "ide" or cyanide, then it ends up being hydroblankic acid. Okay. So if I'm talking about fluorine, which was fluoride, what would the classical name be? Yep. Hydrofluoric acid. All right? So if we have an H in front of a fluorine, it's hydrofluoric acid. Hydrofluoric acid. And I have to say it fluor because the U comes before the O, and I always screw it up if I don't say it that way. Now, the IUPAC name is really the easy name. It describes everything exactly the way it is. Number one, it's aqueous. So we write it down as aqueous. Number two, it has a hydrogen in front of it. So it's aqueous hydrogen. And number three, that's a fluoride, because that's what it's called at the end. Fluoride. Fluoride. So the IUPAC name is actually quite simple. It simply names all of the parts of the acid. It's aqueous, it has a hydrogen, and it has a fluoride. Aqueous hydrogen fluoride. Okay? When we go to the classical name, the fluoride goes into there, and it becomes hydrofluoric acid. Let's try the second one. What's my IUPAC name going to be? Yep. Yep. Aqueous hydrogen chloride. Aqueous hydrogen chloride. Now, chloride. What's it going to be called using the classical naming system? What's it going to be called? Yep. Yep, hydrochloric acid. Hydrochloric acid. Excellent. Work ahead of me if you're starting to get the hang of it. This sulfur one has a little trick to it. All right, so if you want to leave it, I can explain it. You should be able to do the HBr and the HI, and you should also be able to do the HCN, keeping in mind that that CN is called a cyanide. All right, so you can then apply it to the classical name as well. The sulfur one is tricky. It's the classical name that has an extra part. I'm going to do that right now with you. Aqueous hydrogen, and what am I calling this? This doesn't have a trick name to it. It's this one that does. What do we call it? It's a sulfide. 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 Now you might think taking the sulf and putting it in, you'd get hydrosulfic, but it isn't. They add an extra syllable. Yeah, it's sulfuric. It's not just sulfuric acid. That's the next type. It's still hydrogen sulfur or hydrosulfuric acid. Hydrosulfuric acid. Straight up sulfuric acid is a little different. We'll do that next. Okay? So still I have to, because this ends in "ide", it becomes hydrosulfuric acid. So they add the UR in there. They add a little syllable in there. I don't know why. I don't know where it came from historically, why they kept that syllable. Does anybody have the HBr? And I'll take both of them. You just have to read them to me and I'll write them down. Yep. Yep, and I'm just going to write down AQ just for some speed. We get the idea. That's aqueous hydrogen bromide and not hydrobromide acid, hydrobromic acid. Hydrobromic acid. Excellent. Next, does somebody have that one? A little bit of a tongue twister on the next one, but it's kind of fun. We can still do it. All right, Bethany's got to be done back there. What do you got? Yeah, very good. Hydrogen iodide and yeah, hydroiodic acid. Hydroiodic acid. Excellent. How about the last one? Keeping in mind that that's called cyanide. What do you got? Shay, what do you got there? Yeah, it was hydrogen cyanide. Yeah, very good. Hydrocyanic acid. Okay. So if it ends in "ide", like our nonmetals do, and you're doing the classical name, the blank "ide" becomes hydroblankic acid. All right? And that's for binary acids that are made up of two elements, hydrogen and a nonmetal, with this guy being a special case. All right? Okay. Let's move on to the oxyacids. Don't write this down. We're going to do oxyacids, and there's two types. There are oxyanions that end in -ate, or oxyanions that end in -ite. And so now we're looking at the chart on the back of our periodic table because we're looking for those anions. We're looking for those anions that end in -ate or that end in -ite. And if you do a quick look up and down, right away you can see an acetate, and then you can see a hypochlorite, and then you can see a chlorite or a chlorate or a perchlorate. You'll notice how most of them end in -ate or they end in -ite. And how they end determines how we name them. The first ones that I'm going to have you do, actually, let's write down oxyacids, please. And instead of writing down that there are two types, just write down in oxyacids, hydrogen with an oxyanion. Just write that statement right there. It doesn't even need a number. We're putting hydrogen with the oxyanions, which are the things that end in ate or ite. And we're going to deal with them in the next slide. So just write down oxyacids, and that it's hydrogen with an oxyanion. And then we'll go to our next slide, and we will call this the ate anions. So you don't need to write anything extra. So this is the second little kind of helper statement that I'm going to put on the board for you. If it is an anion that ends in ate, all right? So if you're on the back of the periodic table and you find it and it ends in ate, then when you add the H's, it becomes blank-ic acid. Now that's even simpler than the name we just had up above. For the binary acids, right, that end in "ide," it becomes hydroblankic acid. If it ends in "ate," we don't even need to put the hydro in front. You just change it to "ic." All right? So again, tomorrow, I'm going to give you that, I'm going to give you that, and then there's one more that ends with "ite," right? My next slide is going to be, what if you have an anion that ends in "ite"? What do we call that? And like I said, for the quiz tomorrow, I'm going to give you that, those three statements. I'll also be giving you the pH equations, the two pH equations, and I'll also give you the percent ionization equation for the quiz. Put it all on the board. So again, the IUPAC name is a logical name. It's aqueous. I'm going to just put AQ with a dot just to save us from having to write aqueous over and over again. Can you do that on a test? Humor me and write aqueous out completely. All right? So on a test, if I'm asking you for the IUPAC name, write out aqueous. Again, it's starting with hydrogen. Aqueous, hydrogen, and what is this ClO3? From the back of your table, scanning up and down your chart. Yep, Shay? That's a chlorate. So it's aqueous hydrogen chlorate. All right? Aqueous hydrogen chlorate. Well, from my little helper here, if it comes from a chlorate, then that starting point is going to just go with ic. So what do we call this classical name? Yep. Chloric acid. Chloric acid. It seems a little backwards. Chloric acid has oxygens in it. Chloric acid is a bigger molecule than hydrochloric acid, which just has a Cl all by itself. But chloric acid is a smaller name than hydrochloric acid is. It seems backwards, but that's just the way the naming system works. So if the ion ends in ate, and here's the example here, if the ion ends in ate, put an ic ending on the end. So aqueous, hydrogen, what is our ClO4? Again, you're just scanning the back of your table. All of the ions that I give you for this naming, they'll be on the back. What is a ClO4? Jess, what's a ClO4? Sound it out. Use your phonics, Jess. Perchlorate is correct. Perchlorate. Aqueous hydrogen perchlorate, as she said. Chlorate. So this is a perchlorate ion. What's the classical name going to be? Yep. Perchloric acid. Perchloric acid. The 8 becomes an ick. You could probably go ahead and do the rest. You go ahead and work ahead. Give them a shot. Again, aqueous hydrogen. Again, the IUPAC name is very logical. Go ahead, find out what that is. Aqueous. Oh, special case here again, though. Special case on that one. When you do the sulfur version, aqueous hydrogen, and what that is. And this one also, little special case. So if you're not sure, you can leave it blank. But go ahead and finish those off. Find those ions. Aqueous hydrogen, and find out what that ion is. This one isn't special. You can easily do that. You can easily switch it over. You've done them all already? Excellent. All right, let's do one of these, even though you might not be at the bottom. I'll pick on Felicia for no reason. What is the SO4? It's a sulfate. Sulfate. Now, when we had sulfur, the last one, we had to add an extra syllable. That's true here as well. What is this one going to be called? Yeah, sulfuric acid. Good. Sulfuric acid. If you just followed the rule, you'd think it would be sulfic, but it's not. It's sulfuric acid. PO4, what's that? Yep, Bethany? That's a phosphate. Phosphate. And this one also has a little extra to it. What do you think it is? Phosphoric acid? What did you say? Phosphoric acid? I usually write it, you know what, to be honest, I usually write it as phosphoric acid. I don't know if it really is phosphoric acid. That doesn't sound right to me. I always write it as phosphoric acid. Oops. Uh-oh. That silly thing came up. Let's back up the truck. So I write it as phosphoric acid, not phosphoric acid. Phosphoric acid. I don't think it's phosphoric acid, but it could be. To be honest, I've never checked it. I've always done it that way. Phosphoric acid to me is a better way of saying. Sounds better? Somebody do a Google search for me. Educate me here. Is it phosphoric or phosphoric? I always have done phosphoric. Yeah, I really, to be honest, I'm questioning myself at this point. I've always done it the one way, and but I've spelled other things wrong in the past. This wouldn't be the first spelling mistake. It wouldn't be the first spelling mistake that I've. So, is phosphoric acid like? Does it show a formula? Is it H3PO4? Phosphoric acid, H3PO, and it's got an O in it. Yeah. Okay, all right. I thought it was correct, but I've been wrong before. It does sound a little strange. Yep. Probably the way I say it, because I've probably trained myself to say it that way to spell it right. As you know, I say things a little weird sometimes in order to spell it correct. So phosphoric acid. If you had put a U in there, I wouldn't care. But that's the way to do it. How about the CO3? What is that one? What is that one? Hydrogen carbonate. Carbonate, and what will the classical? Carbonic acid, yes. Carbonic acid. So if it's polyatomic, if it's one of these guys that have O's on it, if it ends in 8, it becomes the ic acid. Okay? Again, I'm going to give you this on the board tomorrow. All right, one more type. If the ion ends in ite, I-T-E, the ending becomes O-U-S, us ending. I'm almost done here, so I'm hoping the video will have audio to it, but it's pretty straightforward stuff. Okay. You'd also find the 3U. Anyway, no, you'll be fine. You'll be fine. Okay. So if it ends in ite, if it's an ite ion, then it will become an us ending. Again, the IUPAC naming system is logical. Aqueous, hydrogen, and then we just have to name that thing on the end. Again, you've got the periodic table with the chart on it. You're just scanning up and down to find what the name of that thing is. ClO2. And again, you can go ahead. You don't have to wait for me to do these. If you're getting the idea that the end is going to end up as an us, excellent. Again, with the sulfur, it's going to have the extra syllable in there. Same thing. Just now they're going to end in OUS instead of IC. And so I can play along. Could someone tell me what the ClO2 is? Amy, what is it? What is ClO2? Chlorite. It's a chlorite. I hope it's an ite, because that's what this part of the lesson is about. It's a chlorite. Oops, I put a D there. Ite. So what's the classical name? Chlorous. Chlorous acid. Chlorous acid. Not as common as the ic acids. You've all heard of the ic acids, sulfuric acid, carbonic acid. You've heard of those terms before. But they are indeed acids. If we were to get some chlorous acid, we could test it with some litmus paper. It would be acidic. Aqueous, hydrogen. Somebody have an ending for that? Yep, Bethany. What did you say? Nitrite, because these are all ites. And what is this then? Nitrous acid. Nope, that's nitrous oxide. If you dissolve nitrous oxide in water, you get nitric acid, just like we did with our reactions over there. But it's the nitrous oxide that's put in engines to boost their power output. I don't know exactly what that reaction is. I don't know how the nitrogen affects that. I'm not sure. But that's nitrous oxide. It's a gas. Okay, and this is aqueous, hydrogen, sulfite, because we're dealing with ites. I hope you already figured that out. So what is this one going to be called? What's this one going to be? Yeah, Bethany? Sulfurous acid. We need that UR in there. Sulfurous acid. And take a look, take a look on the back of your charts. Are there any other ites that we didn't use? Any other that end in ite? Shay, did you find one? What was that? Hypochlorite. And so if we added H's to that and we turned it into the acid, what would it be? Hypochlorous acid. So we could also have it for that one. And I think that's the only other one that we haven't covered. Excellent, good. Let's do a couple of examples. Oh, wait a minute. This is a mix-up, and then we do have to do some formulas. So here, let's do these. No, you know what? We've done this to death. Let's jump to here. Let's get the chemical formula now. Let's get the chemical formula. So we know how to name it. Let's now get the chemical formula for these. The chemical formula is determined by the crossover, just like we did when we started doing the simplest naming. So to get the formula is is easy. We just cross it over like we did before. So this is review. I'll give you a chance to create the whole chart. If you think you know what you're doing to cross it over, you can give some a shot. The IUPAC naming system is actually a little easier to get the formula because you don't have to think backwards about what the, what the other element is because it has it right in it. So these are not too bad, but when you're dealing with the classical naming system, you've got to work your way backwards. I just want to finish writing this one down. Acid. Again, I've stated this many times. You will be given that on the board tomorrow, okay? And then your periodic table, obviously. So again, when we get a formula, we need to determine the front part and what its charge is, and the end part and what its charge is, and then we just cross it over, right? These are actually very easy because what's the front part of an acid every time? H, with a plus charge on it. So I'm going to do this twice, showing you where it comes from. H with a plus. Sulfide. Now you got to remember the 8s and the ites are on the back of your table, but the ides are these guys with their regular charge. Okay? Cyanide being the special case. So sulfur, does anybody remember what the charge is on a sulfur ion? Yep. 2. It's -2, right? Because it gains 2 to get the full outer shell. A little review. Group 17 is -1. Group 16 is -2. 15 is -3. And then carbon and silicon are -4, but I don't think we'll be dealing with any of those. So sulfur, sulfide, has a charge of -2. We cross the charges over, and we ignore the charge. We just bring the numbers, 1 and 2, puts a 2 down there and a 1 down there, and we don't write down the 1s, right? Remember, we leave the 1s out. So this is H2S. We cross it over. You don't need to write that crossover every time. Once we get good at it, we can do that in our heads. Chromate. Where are you going to find that? On the back. So I'm going to write down the H. And now I need a chromate. What do you got? So CrO4, and that's a 2 there. So you brought it down and you wrote the 2 right there. Excellent. There will never be brackets because it's always a 1 on the back end. There's never a 2 or a 3 on the back end. So for acids, there's never brackets on the back like we had way back when we started doing that stuff. So acids are really pretty straightforward. Again, hydrogen, H. You have a nitrate there. Well, I can be patient. So I only need H1, right? So what's the formula then for the nitrate? No, I'm doing ite. What? NO2? NO2, and the charge on that NO2 was is 1, so I cross over and the 1 is there, and that's it right there. HNO2. Excellent. Now, nitric acid, you almost have to think now in reverse. Here it is here. So what did it start as? Yep. Nitrate. So you go from ick back to 8. So you're thinking nitrate. Nitrate. You don't have to write it down, but that's what you're thinking. We're getting the nitrate. We're crossing it over. Amy, what do you got? HNO3. Okay? Us. What are we thinking? We're thinking ite. So we're looking for a chlorite, right? Again, you don't have to write that down, but we're looking for a chlorite. Then we're putting the H on it and crossing it over, and we're getting the formula, and someone other than Amy's going to tell me an answer. John's going to tell me an answer. HClO2. HClO2. Okay, that space isn't significant. It's just I was writing it that way. Nothing important there. Hydroic. What are we thinking? If we go in reverse from our hydroic. Hydroic. Oh, excellent. Formula HBr. HBr. We're thinking bromide, right? Because the hydroic becomes bromide. There's our bromide right there, -1 charge HBr. Okay? All right. Excellent. So that's the acids. Just a little review of bases, and then we'll be done. The bases that we're going to deal with are always going to be hydroxides. So again, all we have to do is name them, and getting the formula, all we have to do is cross it over. Now again, technically, in order for bases to be basic and exhibit their basic properties, like turn some bromothiamol blue blue, we need an aqueous in front of it. But you know what? If you didn't write down the aqueous, I would be okay with it. But technically, this should be aqueous. Well, what is this stuff? Sodium hydroxide. Sodium with a hydroxide. The technical name, if it's behaving as a base, is aqueous sodium hydroxide. But if you just wrote sodium hydroxide, I wouldn't take a mark away or anything like that. That's great. Sodium hydroxide. To get the formula, again, we're just ignoring the aqueous part, but we do have to cross over. So we do have to use the crossover method. It is an ionic compound, so we do have to cross over. We have a calcium and we have a hydroxide, and now I need to look at some charges. What do I have to do? What do I have to do? Yeah, I think. Yeah, correct. Outside of the brackets. Outside of the brackets. Many people make the mistake of doing something like this, okay? And I think the reason many people make that mistake is because they don't see a number behind the hydrogen, so they think, oh, I don't need the brackets. But we need the brackets because it's actually 2 hydroxides that are stuck to this. In this formula, there are 2 oxygens and 2 hydrogens. In this incorrect formula, there are 2 hydrogens, but only 1 oxygen, and that is not calcium hydroxide. So you must have the brackets when dealing with hydroxides, and you've got to cross over the 2. Questions or concerns? Okay, so that's the end of my note. I don't even have, go see the worksheet because it is on the Google Classroom. You've got your own copy. You can type those in, that type of thing. I do have answers, I believe, down below it. It's just a PDF where I've quickly written in the answers. So at this point, you've got a half an hour to work on that sheet to maybe look back at some pH and POH, sorry, no POH for you guys, just some pH calculations. Again, let me just stop my recorder here and I'll take a question and then I'll do my little summary here. Just so we don't need to listen to all of this going on. Hopefully the audio